So remember last time I defined what are cohomology groups. If G is a group and A is an abelian group on which G is acting from left. So we'll see some relation between the first cohomology group and extensions of A, or more precisely split extensions of A. I will define what these terms mean. So by an extension, we mean a short exact sequence of this form. So because A is abelian, I'm writing it additively. So 0 is the identity. And I'm writing G as multiplicatively. So 1 is the identity. So this is a short exact sequence is called an extension of A by the group G. So E is the extension. So this is a short exact. E is called an extension of A by G if there is a short exact sequence of this type. And so now let me call this map part. So throughout I will denote this map pi. And now observe that you have this action of A, or say uh, E on A, that is, so you take an element of E, you simply take the conjugation, which will land you inside E, but if you apply pi to it, you will get, because pi is a group homomorphism. And remember, pi of A, you can identify A as the kernel of pi, right? Because of the short exactness. So this becomes 1, and this becomes this. So this is 1. So again, this thing is in the kernel of, or maybe I should write it 0 because A is written additively. So this becomes in the kernel of pi, which is A. So indeed, E is acting on E, and this action is trivial on A, right? Because A is anyway abelian. So if E is, the small e is from coming from capital A, then E inverse is same as just A. So this action is, so we have from this an action of E on A, and that's factoring through A. So indeed we are getting an action of E mod A, i.e. an action of G on A. So we get A is a G mod. Okay. So that's a nice observation because we need a G structure on it to make sense of the cohomology groups. And now, so let's see. So last time, we know these are the one co-cycles quotient by one co-boundaries. So precisely, if F is an element of this, then it has this property that if you take any two element GH from the group G, then this behaves like this. And sometimes this is also called crossed homomorphisms. Because in homomorphism there is just f of G plus f of H, but there is a twist by an action of G here. So sometimes this is called cross homomorphism. And if A is a co-boundary, that means A is image of something, or if I should say image of this map del A, or some element of A. So this means just that f of G is for some, for all G, for some A. Yeah. So now let's see how we can identify the elements of the H1 to some split extensions. And this extension, let me denote it by say star because we will need it again in future. So is split if there is you can imagine what should be the case, that in that case you can write E as a group, I mean as a semi-direct product of A and G. So in other words, there is a homomorphism you can call S, which is sometimes called section, in the other direction. So this means just when you compose this, it gives identity on the group. This S is called a section. So this S is a section of pi, and it's a group homomorphism. Yeah. So let us now take some notations. So our principal objects will be automorphisms and inner automorphisms, but not all of them. Some specific type of inner automorphisms and automorphisms of the extension E. So by specific, I mean so you take all the automorphisms from of E that when you restrict it to A becomes identity, and if you apply pi to it, it gives you the same thing. This should hold for every element. And for inner automorphism, uh, you take all the automorphisms of E again, but these are of this form. So these are like, so phi of E is A inverse for some A. So these are inner automorphisms, but you are conjugating via some element of A. So these will be our main objects of study, and eventually what we will show, let me state it as a theorem, that the first cohomology group is in fact you take all the automorphisms of this property that it restricts to identity on E, and you quotient it out by the inner automorphisms of this particular type. So this will be our main aim of this video, but it's the proof is quite elementary, although it's a bit long and tedious checking of certain easy things. So I will split it into two parts because otherwise the proof would be too long for one video. And so let's see how we can do it. And the second thing that I will show after we finish this, that there will be a consequence, or let me write it as a corollary, that this will imply that the first cohomology group is in bijection with, you say, all the splitting of our extension star modulo a certain conjugacy relation of A. Let me denote it by some tilde. I will define all of them. So these are sometimes together this equivalence class. So the collection of equivalence classes are called A conjugacy classes. Of splittings of star. Yeah. So now let's slowly build up towards proving this theorem. Proving this corollary from the theorem is kind of easy and not very difficult. So let's slowly build up towards the proof of the main result. So eventually we'll need isomorphism. So, and remember H1 is just quotient of Z1 and by B1. So let us start by taking a map in the following way. From this to Z1, let's denote it by alpha. And so let's see, take an element phi of this from this set automorphisms, and now observe that by a condition pi of phi e is same as pi e. So we have this phi e inverse of pi becomes 1. So this is in A because kernel of pi we have identified with A, right? So for this, and remember what are the elements of Z1, because we want to map this phi to something in Z1, and the elements of Z1 are nothing but a specific kind of maps from G to A satisfying the co-cycle condition. So that is kind of easy because you take phi and you take a define send it to say f phi, which is just a map from G to A by so let's see how we can define, and we are identifying G with E mod A. So let us see if we can define at least a map from E to A, then we can sum up uh, take say if this map is acting nicely enough on A, you can take the quotient and you can pass through the quotient to get a map from G to A. So let me denote this map. In fact, let me denote this thing by not f of phi because this is just alpha of phi. So you consider this map from E to A by, already we have for each element an assignment here. So simply just take this. This is a well-defined element of A, no problem in that. And moreover, if A is, or I should say, E is coming from A, then what will be this element? This element, if you apply pi on it, this is just, I should say, mm, or maybe not this. These are just easy checking this elementary things. So let's see what more we need. So we need this map should be stable under A so that we can factor through it. For that, just do this thing. Take this and take E of A, okay? Because we are showing that it is stable on each coset. So take an element of the coset, and this should be just phi of EA times EA inverse, which is A inverse E inverse. This is just phi of E and phi of A, and that is just A because remember phi restricts to identity on A. So phi of A becomes A, and we are done. So it eventually factors through A, defining a map from, let me denote it by phi f phi tilde, defines a map from this to A, and this is just G. So eventually this map alpha sends phi to f phi tilde, is well defined. Oh, but now again, to show everything, we also need to check that this map satisfies the co-cycle condition. So this is not enough. So this if f phi tilde uh, satisfies the co-cycle condition, satisfies, or let's write it in short, is and one co-cycle. So let's see how we can do it. So remember, co-cycle means we have to show this relation. What is just this? This is an element of co-cycle. So to show this, let's do the routine checking. Take this. This should be just phi of gh, which is phi of g, phi of h, phi of h inverse g inverse. Next, you can write this thing as phi of g, g inverse. Keep it as it is. This is g. There is phi of H, H inverse, G inverse, and now, so this thing is, so let's just write this thing as phi G tilde of G. This is G dot phi, or I should say F phi tilde G inverse, and that is just this. And what is this? Because remember, we are taking the action by via conjugation, and the action was originally from E to A, but we have eventually factored through to get an action of G on A, and that action is again via conjugation. So this actually means that G acting on F tilde this. Okay. And now let's compare this to our this. So if you write it multiplicatively, you will get what? You will just get F of GH. If you write it multiplicatively, you will just get this, right? And that is exactly what we get here. So we are done. So this F phi tilde, whatever it is indeed satisfies the co-cycle condition. And in the opposite direction, so we need a map. So our goal is to show that this Z1 is isomorphic to the automorphism group of E's that satisfies those two extra conditions. So we have already done one part, and so let us now define in the opposite direction. And let's see, so now we need to define a map beta from this to automorphisms of E with this notation. So let's take an element, let me call it A. So A is, remember, a map from G to A satisfying the co-cycle condition, and this will be beta of A, which should be a map from E to E, in fact an automorphism from E to E that satisfies those two extra conditions. And for that, it's easy to check. You take an element E, and so remember, domain of A is G, so you push this A via pi to get an element of G. You apply A on it as you should, and you take this extra product of it. So you need to check a bunch of things here. First of all, that this beta of A is an automorphism of E. Secondly, its identity on A, and third is pi composed beta of A is pi of A. Those two extra conditions. So let us see how we can do it. One part is easy. So if say x is coming from A, then you have beta ax, which is just a of pi of x dot e, which is a of 1 dot e. And now this is a small exercise you can do, that is to show a is normalized, or in other words, a takes 1 to 1. It's really easy to show just using the co-cycle definition. You can get it. So this becomes a. So, or I don't know what notation I'm using. This should be all x. So you get beta of a restricted to a is identity. Okay. Secondly, you take say pi compose beta of e, which is just pi of a of pi of e times e, right? And now this element is in a, which is kernel of pi. So if you apply one more time pi on it, just vanishes. So you will left with pi of. So we are done. The second condition is done. And so now this is an easy check. So check that beta of A is a homomorphism. Just use the definition. So is a homomorphism that is identity on A and induces identity on G. So it will force that this is an automorphism. You can easily check that. Take it as an exercise. Just this is group theoretic things. And now so we have maps in two directions, and showing composition is identity is really easy because you take alpha compose beta, you take a cocycle, take an element G. So these are beta of A. You take say G inverse, right? Or I should say G tilde. Yeah. And this is just A of G tilde, the inverse of G. So one side is identity and the other side is equal easy. Just use the definitions. You take phi G tilde, that will be just alpha of phi of G tilde. So by the way, G tilde is just this. So then again pi of G tilde, G tilde inverse and G tilde, which is again pi of G tilde. So indeed we get that this is also identity. So eventually we get that this is isomorphic to this. So I will stop this video here. Next time I will show, by the way, that the inner automorphisms is isomorphic to, as you can guess already. So that will eventually prove that the quotient is isomorphic to the first cohomology quotient of this via this. So I'll stop.